So, in the last lecture we were examining the definition of the stress. The stress is defined as the force exerted per unit area, okay, sigma xz for example, is the force exerted per unit area in the x direction at a surface whose outward unit normal is in the z direction. Similarly, sigma xx is the force per unit area in the x direction at a surface whose outward unit normal is in the x direction, and so on. Okay. So, the stress has two directions associated with it. One is the direction of the force and the second is the direction of the perpendicular to the surface. Okay. So, the stress has two directions associated with it. Therefore, it is a second order tensor. It has two indices and two unit vectors. The first unit vector and the first index shown here on the left corresponds to the direction of the force, which is a vector. The second unit vector and the second index corresponds to the direction of the perpendicular to the surface or the direction of transport, which is shown here in blue. Okay. So, it has two fundamental directions associated with it. And since there are three possibilities for the direction of the force, three possibilities for the direction of the unit normal, there are a total of 9 components of the stress, which we had written out here in tensor in matrix notation. Okay. Which we had written out here in matrix notation. The first matrix of unit vectors is the direction of force. The right matrix is the direction of the perpendicular to the surface, and the square matrix contains the components of the stress. Okay. So, that is the definition of the stress. And at a surface within a fluid, right, at a surface within a fluid, if I want to find out what is the force exerted, I would take the stress tensor and dot it with the unit normal. Dot the second index of the stress with the unit normal. Okay, and I will get, when I dot a second order tensor with a vector, I will get a vector because the second order tensor had two directions. And when I dot one of those directions with a vector, that becomes a scalar, leaving back a vector. Okay. And that is the force that is exerted on the surface. Okay. Sigma dotted with n is the force times delta s, of course, because sigma is a force per unit area. And you can easily see that this force reverses in sign if the unit vector reverses in sign, okay, because f of minus n is equal to minus of f of n. Okay. The force for a surface with outward unit normal n, in this case the surface A, okay, the surface of the volume A has an outward unit normal in the plus n direction. The surface for the adjoining volume B, that has outward unit normal in the minus n direction. Okay. The stress at this location is a single valued function, it has a single value. Okay. Therefore, the force exerted on the surface on the volume A, okay, at this surface is negative of the force exerted on the volume B at this surface, because the direction of the unit normal for these two volumes are negative of each other. Okay. Therefore, this satisfies the Newton's third law that the forces have to be equal and opposite, okay, on both sides of a surface. Okay. And I had also divided the force into a normal force and a shear force. Now, there is an important constraint on the form of the stress tensor due to angular momentum conservation. Okay. I will illustrate that by looking at a differential volume . Okay. I will draw that a little bit bigger so that it is easier to explain. Okay. This is a differential volume, but I am drawing it a little bit big so that I can explain easier. It has side, this location is x, y, z. Okay. At the location x, y, z, I have a differential volume with sides delta y in the y direction and delta x in the x direction. Okay. and I can write down the stresses at this volume. Okay. So, I will assume that it has a differential length delta x in the x direction, delta y in the y direction, and delta z in the plane in the direction perpendicular to the plane. Okay. The delta z is the third direction, which I have not drawn here. Okay. On the surface, I can find out what is the angular momentum balance for this differential volume based upon the forces that are exerted on this surface. Okay. You can see that at the right face, the unit normal is in the x direction. Okay. The unit normal is in the x direction. Therefore, the force in the plus x direction is sigma xx. Okay. Because the unit normal is in the plus x direction, the force here is sigma xx, and the force in this direction, in the y direction, is sigma yx. Okay. At this right face. At the top face, the unit vector is in the plus y direction. Okay, the unit vector is in the plus y direction. Therefore, the normal force is sigma yy, okay, and this is the shear force. The force per unit area in the x direction acting at a surface whose outward unit normal is in the y direction. Okay. So, these are the normal and the shear forces at these two faces. At the left face, unit vector is in the minus Ex direction. The outward unit vector is in the minus Ex direction. Okay. And therefore, the force per unit area is minus sigma xx. Okay, because the unit vector is in the minus Ex direction, and the unit vectors and the force per unit area in the y direction is minus sigma yx, because the unit vector to the surface is in the minus Ex direction. And similarly for the bottom face, okay, this is sigma yy. The force at this face is equal to minus sigma yy, because the unit vector is in the minus Ey direction, and this is equal to minus sigma xy. Okay. Okay. So, what is the contribution to the torque about the center? Okay. About the center axis of rotation, we will consider as the along the z coordinate passing through this location x, y, z, okay, perpendicular to the plane of plane. Okay. What is the contribution to the torque? Okay. So, if I write down the contribution to the torque from each of these individual contributions, okay, note that according to the right hand rule, the torque is in the anti-clockwise direction is positive. Okay. The torque in the anti-clockwise direction is positive. Okay. So, therefore, contribution from right face to the torque. Okay. The torque is going to be equal to the tangential force multiplied by the distance from the axis of rotation. Okay. The tangential force times the distance from the axis of rotation, okay, that is going to be the contribution from the torque. So, the tangential force here is sigma yx at x plus delta x by 2. Okay. This is the force per area, okay, times the surface area, that is going to be equal to delta y into delta z. Okay. Okay. So, this distance is delta y, okay, and delta z is the distance in the perpendicular to the plane. Okay. So, that is going to be the contribution to the torque from the right face, okay, at x plus delta x by 2. Okay. Okay. So, this is the torque, I am sorry, I should add here. So, the torque is going to be the force times the distance from the axis of rotation. Okay. Force is stress times area, okay, sigma yx times delta y delta z times the distance from the axis of rotation, that distance is delta x by 2. Okay. Okay, so, that is going to be the contribution to the torque from the right face. Okay. contribution from left face. Okay. It is going to be the tangential force at the left surface, that is minus sigma y x at x minus delta x by 2 into the surface area times the surface area delta y delta z into the displacement from the axis of rotation. The displacement from the axis of rotation on the left face is minus delta x by 2. Okay, so that is the contribution to the torque from the right and left faces. Okay. Contribution from top. Okay. Note that stress is positive in the counterclockwise direction, whereas the torque is positive if it is in the counterclockwise direction, whereas you can see that on the top face, the sigma xy, if it is in the plus x direction, it tends to exert a force in a torque that is clockwise around the center of rotation. Therefore, the contribution to the torque from the top face is going to be equal to minus sigma xy at y plus delta y by 2 into, in this case, the surface area is delta x delta z into delta y by 2. Okay, surface area of the top face is delta x times the perpendicular distance delta z times the distance from the axis of rotation, that is delta y by 2. Okay. And finally, contribution from bottom. Is going to be equal to, in this case at the bottom face, the force is minus sigma xy in the clockwise direction. Okay. Therefore, the contribution to the torque in the counterclockwise direction is going to be equal to plus sigma xy. The force is minus sigma xy, but it tends to rotate around this center point in the clockwise direction. Okay. So, therefore, the contribution to the torque in the counterclockwise direction is going to be equal to plus sigma xy at y minus delta y by 2 delta x delta z into minus delta y by 2, the displacement from the center. Okay. So, putting these together, okay, I can write that the rate of change of angular momentum times the moment of inertia, okay, about the z axis, I z times d omega by dt, okay, is equal to, okay, you can see there is a common factor of a half, okay, into delta x, delta y, delta z. If I add up all of these, okay, if I add up all of these, I will get a common factor of half times delta x, delta y, delta z, and then in the brackets I will get sigma y x at x plus delta x by 2 plus sigma y x at x minus delta x by 2, okay, minus sigma x y at y plus delta y by 2 minus sigma x y at y minus delta y by 2. That is going to be the angular momentum conservation equation in this case. Moment of inertia times the rate of change of angular velocity is equal to the sum of the torque. And we calculated the individual contributions to the torque from the from the right, left, top and bottom faces and added them all together. This torque is in the counterclockwise, in the clockwise, counterclockwise direction. The anti-clockwise direction is positive. Okay. Therefore, the angular velocity is also positive in the anti-clockwise direction. What is this moment of inertia I z? Okay, is equal to integral, okay, over the volume of any differential mass element at some location r, okay, of delta m, okay, mass element or okay. Integral of the volume of rho times the distance from this axis of rotation square. Okay. Okay. This integral of the volume of the density times the distance square from the axis of rotation. Okay. That is the moment of inertia. Okay. So, if I take a coordinate system x prime y prime centered at this location, okay, this is going to be equal to integral dx, integral dy, integral dz. Okay. These are primes, okay, of rho times x prime square plus y prime square, okay, going from minus delta x by 2 to delta x by 2, minus delta y by 2 to delta y by 2. Okay. That is the integral over this entire volume of the local mass. Okay. The local mass is rho times dx prime times dy prime times dz prime, where the volume is dx prime dy prime dz prime, that is this volume. Okay. Okay, dv is equal to dx prime dy prime dz prime, and the distance from the center of rotation r square will be equal to x prime square plus y prime square. Okay. And that is how you calculate the moment of inertia. Okay. And it is relatively easy to see that by carrying out this integral, okay, over this entire volume, that this is equal to rho into delta x square plus delta y square, okay, into into delta x, delta y, delta z, the whole divided by 12. Okay, it's a factor of 12 that comes out. Okay. Okay, so that is the moment of inertia, okay, for this differential volume around the axis of rotation, that is in the z direction. Okay. Therefore, I can write the momentum conservation equation as rho into delta x square plus delta y square, delta x, delta y, delta z by 12 into d omega by dt is equal to half delta x, delta y, delta z and you can easily see that this factor of delta x, delta y, delta z goes to 0. Okay. And if we take the limit delta x, delta y and delta z go to 0, in this limit you can see that the moment of inertia is proportional to delta x square and delta y square. Okay. So, that actually goes to 0. Okay. On the right hand side, okay, you do not have any quantity that is going to 0. This implies that this entire right hand side has to be equal to 0 in the limit as delta x, delta y, delta z go to 0 for momentum conservation to be satisfied. Okay. So, it has to be 0 for momentum conservation to be satisfied. Okay. So, if I take the limit delta x, delta y, delta z going to 0, the left hand side is just equal to 0. On the right hand side, I have sigma y x at x plus delta x by 2 plus sigma y x at x minus delta x by 2 in the limit as delta x goes to 0. This just becomes equal to sigma y x itself, okay, multiplied by 2. Okay. And I have a factor of half here. Okay. So, this is equal to sigma y x minus sigma x y. So, that is the requirement for angular momentum conservation about the z direction. Okay. You can do the same calculation for angular momentum conservation about the x and the y directions, okay, and you will get about the x direction you will get sigma xz minus sigma zx, and about the z direction I will get sigma, no, z direction sigma yx, so about the y direction. Okay. So, this is about the y direction, and then I have the x direction, okay, sigma zy minus sigma yz. Okay. All of these have to be equal to 0. Okay. What that implies is that sigma xy equal to sigma yx, sigma xz is equal to sigma zx, and sigma zy is equal to sigma yz, which implies that the stress tensor, okay, that the stress tensor is a symmetric tensor. Okay. The off diagonal elements are all equal if you interchange the indices. Okay. Therefore, the stress tensor is a symmetric tensor. This is a requirement of angular momentum conservation. Okay. The stress tensor is a symmetric tensor. So, therefore, the original stress tensor had a total of 9 components, and then I showed you that in order to satisfy angular momentum conservation, 3 of those components are equal to their transpose. Therefore, there are 6 independent components in the stress tensor. Okay. There are 6 independent components in the stress tensor. Okay. Now, what if there is no flow? Okay. The absence of flow, okay, there could be a pressure. Okay. The pressure acts in the direction of the unit normal, and it is perpendicular along the inward unit normal. Note that the stress tensor was defined with respect to the outward unit normal, whereas the pressure acts perpendicular along the inward unit normal. Okay. So, the stress due to the pressure can be written as sigma is equal to, okay, minus P or I can write this in summation as minus E x P E x minus E y P E y. Okay. So, therefore, the stress due to the pressure in the absence of flow has only diagonal elements, and all 3 diagonal elements are equal to minus P, where P is the pressure. Okay. Okay. All 3 diagonal elements are equal to minus P, where P is the pressure. Okay. And it is easy to show that then the force exerted at a surface sigma dot n, okay, which will be equal to minus E x P E x. Okay. Okay. Dotted with the unit normal n x E x plus n y E y plus n z E z. That is the force per unit area. Okay. That is the force per unit area acting a surface whose outward unit normal is in the n direction. Okay. Here I have to dot the second, okay, unit vector with the direction of the unit normal. Okay. I have to dot the second unit vector with the direction of the unit normal, and what I will get is minus, okay, P n x E x minus P ny Ey minus P nz Ez. Okay. Just doing the dot product. Okay. And this is equal to minus P into n vector. Okay. So, therefore, due to the pressure, the force per unit area acting at a surface is equal to minus of the pressure times the outward unit normal. Okay. So, it is acting along the inward unit normal. Okay. So, in the absence of any force, okay, in the absence of any flow, there is still a pressure which acts along the inward unit normal. Okay, that is, and so the magnitude of the pressure is the same, independent of direction of the surface, independent of orientation of the surface. The direction of the force exerted due to the pressure is along the inward unit normal. Okay. Okay. And if you actually take n dot sigma dot n, okay, this is equal to minus P. Okay. You recall that I defined n dot sigma dot n as the normal stress, okay, the normal stress. In the absence of flow, the normal stress is equal to the negative of the pressure, because the normal stress is defined to be positive along the outward unit normal, whereas the pressure acts along the inward unit normal. Okay. So, I have discussed the pressure for you, some of its properties. Okay. The fact that I am sorry, I have discussed the stress tensor for you, some of its properties, the fact that it has to be symmetric. In the absence of flow, you have a pressure which is an isotropic pressure. Okay. So, this matrix, okay, so I told you that this stress tensor is often written as in just matrix form as minus P 0 0 0 minus P 0. Okay. This can also be written as minus P into the identity matrix. Okay. And this is often written in the notation that is used for the identity matrix as the identity tensor. Okay. I is a diagonal tensor which has all diagonal elements equal to 1 and all off diagonal elements are 0. Okay. So, this is the notation that is used for the pressure. It is minus P times I, where I is the identity tensor. When you dot it with the unit normal, you get the force acting with magnitude minus P times the surface area in the direction along the inward unit normal to the surface. Okay. So, because the pressure is always compressive. Okay. Pressure is always compressive. Okay. So, this is the stress tensor, two directions, direction of force, direction of the perpendicular to the surface. This in the constitutive relation has to be related to the gradient of the velocity. That gradient of the velocity is also a tensor, okay, and we will examine the velocity gradient tensor or the rate of deformation tensor in the next lecture. Try to separate it out in a similar manner into different components and examine what each of these individual components mean. So, this velocity gradient tensor I will discuss in the next lecture before relating the stress tensor to the velocity gradient tensor. I will continue this in the next lecture. I will see you then.